One of the most well-known concepts in electricity is the Coulombs Law. In this video, we will solve problems involving Coulombs Law in one dimension. Coulombs Law states that the magnitude of the force between point charge QA and point charge QB, separated by a distance r, is proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. Or mathematically, we can say F is equal to K times QA times QB over R squared, where F is equal to the force measured in Newton, K is the Coulomb's constant with a value of 9 times 10 raised to 9 Newton meter squared per Coulomb squared. QA and QB, take note that we'll be using the absolute value of these two charges. They are measured in terms of coulombs, and R is the distance between them measured in meters. Let's try to understand this one by imagining two charges. Let's say charge QA and then charge QB separated by a distance. Let's say the charge of QB is negative. How will it react if the charge of QA is also negative? Remember that like charges, they repel. So we can say that QB will try to move away from QA, going to the right, while QA, same idea, it will also go away from QB, going to the left. But what if we have two different charges, negative for QB, positive for QA? Well, unlike charges, they attract. So we can say that QB will go towards QA. Same thing with QA, it will go towards QB. And by using these concepts, we are now ready to solve some problems. We can apply the following strategies in solving Coulombs Law in one dimension. We will discuss one by one as we solve a sample problem. Let's try this one. Sphere A with a charge of positive 6 microcoulomb is located 4 cm to the left of sphere B, which has a charge of positive 3 microcoulomb. Letter A. Find the force on sphere A. The first thing that we have to do is to draw a diagram of the charges, and we have to identify the charge of interest. We can also do step number 2 by identifying all the given and convert all units to SI. So we have our first charge here, QA, and then our second charge, QB, separated by distance 4 centimeters. We have to convert it to meters, that is 0.04 meters. QA is positive 6 microcoulomb, that is the same as 6 times 10 raised to negative 6 coulombs. The positive 3 microcoulomb for QB, that is the same as 3 times 10 raised to negative 6 coulomb. And we move on to step number 3. We apply Coulombs Law and identify the direction. And so we bring out our Coulombs Law here. And since our charge of interest here is sphere A as given in the problem, the force that we are looking here is the force of QB on QA. So we can say the force of B is equal to 9 times 10 raised to 9 Newton meter squared per Coulomb squared. That is your Coulomb's constant, multiplied by the absolute value of 6 times 10 raised to negative 6 coulombs, that is your QA, times the absolute value of 3 times 10 raised to negative 6 coulombs, that is your QB, divided by 0.04 meters squared. And so, the force of B is equal to 101.25 newtons. The Coulombs Law will only identify the magnitude of the force. How would we know the direction of the force? Well, since we have two positive charges, we can say that QA will be repelled by QB. Therefore, QA will move away from QB. And that will give us the direction of our force. And let us not forget that in one dimension, vectors rely on a straight line, either in horizontal, or that is your x-axis, or vertical, that is your y-axis. And by convention, we say that if a vector will point towards your left, it's negative. If to the right, it's positive. If it points up, it's positive. And it's negative if it points down. And since our force B is pointing towards your left, so as your final answer, the force of B is equal to negative 101.25 newtons. Or you can say, therefore, the force of B is equal to 101.25 newtons to the left. Now the negative sign there will tell you the direction. Now, what if sphere C with a charge of positive 2 microcoulomb was added and was placed 5 centimeters to the left of sphere A? Find the net force on sphere A. So we will include QC in our drawing, and since our charge of interest is still QA, for us to identify the net force on sphere A, we need first to find all the forces that will act on sphere A. And these are the force of QB on QA and the force of QC on QA. We already computed the force of B, which is negative 101.25 newtons. So we have to solve for the force of C. So the force of C on A is equal to K times the absolute value of QA times the absolute value of QC all over 2R squared. And this will give us 43.2 newtons. And for the direction, since QC and QA are both positive, we can expect that QA will be repelled because of the force of QC. Therefore, the direction of FC is towards the right. And to identify the net force on sphere A, we have to find the resultant force by identifying the sum of all the forces, and later on we will determine the final direction. So the net force on sphere A is equal to the force of B on sphere A plus the force of C on sphere A, which is equal to negative 101.25 newtons plus 43.2 newtons. And so, our net force is equal to negative 58.05 newtons. And for the direction, we can obviously say that the force of B is much stronger than the force of C on A. That's why we have here a negative F net. And for our final answer, the net force on sphere A is equal to 58.05 newtons to the left. How about if we have a problem like this? Find the net force on point A in the figure below. R1, R2, R3, they are all the same, which is 2.5 centimeters. If you notice that our figure is diagonal, what we're gonna do here is to rotate the figure so that all the charges appear to be in your typical X or Y axis. For this example, I will be doing it in vertical. Therefore, my up is positive and my down would be negative. The figure is already given. The only thing that we need to do is to convert 2.5 centimeters to meters, and that is 0.025 meters. Also, our charge of interest is point A, meaning to calculate the net force on point A, we need the force of B on A, the force of C on A, and the force of D on A. To solve for these forces, we will be using Coulombs Law. So for FB, that is equal to K times the absolute value of QA times the absolute value of QB divided by R squared. This will give us a force of 129.6 Newton. We will try to identify the directions later on. Let's proceed to force of C. So for FC, that is equal to K times the absolute value of QA times the absolute value of QC divided by 0.05 meters squared. This distance is from point A to point C. And so our force of C is equal to 32.4 newtons. For force of D, that is equal to K times the absolute value of QA times the absolute value of QD divided by 0.075 meters squared. Again, that's the distance from point A to point D. And this will give us a force of 14.4 newtons for FT. Now for the directions, for force of B, since QA is negative and QB is positive, QB will try to attract QA towards QB, and therefore the direction of FB is going down. So we have negative 129.6 newtons. How about the force of C? Since both of them are negative, QA will be pushed away by the force of QC, and therefore the direction of FC is upward. So we have positive 32.4 newtons for FC. And lastly, for force of D, since QD is positive, it will try to attract the negative QA. Therefore, direction of FD is downward, giving us negative 14.4 newtons for force of D. For the net force on point A, we have FB plus FC plus FD, that is equal to negative 129.6 newton plus 32.4 newtons plus negative 14.4 newton, and the net force is equal to negative 111.6 newtons. The negative sign will tell us that if we add all the forces, FB, FC, FD, they end up pointing downwards. And therefore, our final answer is 111.6 Newton downwards. You might say that the downward direction does not make sense because we started with diagonal figure. So you can also say direction is towards B, C, and D, and that would also be acceptable. And that's it for this video. I'll see you again next time. Happy solving!